So far in subtopic D.4 we've been looking at main sequence stars. We're now going to look at what happens after main sequence stars have finished fusing hydrogen. So we're going to start first of all though looking at that last phase. So in main sequence stars, when its hydrogen core is used up, and keep in mind here we're talking about all of the hydrogen in the core itself, not necessarily the entire amount of hydrogen. So the first thing to be aware of there is that we're going to see that the radiation pressure decreases. So radiation pressure can't balance gravitational forces, and the result of that is that the star will, or the core itself, will collapse. So there's the first key thing. One of the other things there, as it collapses, it's also going to heat up. The consequence of that, a couple of consequences. The first is that helium in the core starts to fuse. So we then get fusion of helium itself. Any other hydrogen that's around will then expand outside the core. So hydrogen expands surrounding the core. So we've now got a helium core, and that basically, once all of those processes have occurred, the star becomes a red giant. So we've sort of stepped along in this process, and now we've got a red giant star that's been formed. Now, with hydrogen having been used up and helium now fusing, we get a successive sequence of fusion of hydrogen. So successive fusions of helium, successive fusions of helium, and if we're thinking about helium nuclei being 42He, the other name that we might give that is the alpha particle. So if you were to look up this particular process, you might look for the alpha sequence. So there's a number of different elements that are created here. So these successive fusions of helium nuclei create larger and larger nuclei. We might have a look at what that sequence is in class, but ultimately we're leading to the point that we get to two particular elements, and if you look in the textbook it only refers to one, but we're going to look at both iron 52 and nickel 56. So until those two are produced, we sort of see this increasing size of the nuclei that are being produced by the fusion. So these are two of the most stable isotopes of all of the isotopes that we come across. Notice that I'm saying two of the most stable, not saying that they are the most stable. In fact, the most stable is nickel 62, but we don't worry about nickel 62 here because it's fairly low proportions in stars. It's not all that abundant at all. So these are two of the most stable nuclides, having a very high binding energy per nucleon. So what that means is that it's hard then to fuse, once you get to iron 52, nickel 56, it's hard to produce anything larger than that. And the reason for that is, so larger nuclei than this, or than these ones, can't be produced by fusion and the reason for that is that energy actually would need to be added in order for that fusion to occur. So I'll just make that note. Or energy would need to be taken in, is another way to think of it. In order for those larger nuclei to be fused, or to be a product of fusion. Taken in. So there's then two processes that we need to have a look at here. One of them we'll deal with in this video, the next we'll deal with when we start to look at supernova. There is actually a process by which larger nuclei can be formed. I mean, if we think about it, we have a lot of these larger nuclei on Earth, so there must be a way for it to occur. And that process that we're going to look at here is known as neutron capture. So in neutron capture, larger nuclei can actually be formed. And the reason this occurs is because the fact that a neutron is neutrally charged, or there's no charge on it. So when we're talking about looking at the size of the nucleus, we deal with charged particles being shot towards the nucleus and they're being repelled by electrostatic forces. However, as neutrons are not charged, they can easily get close enough to a nucleus so that the strong nuclear force can start to take over. Or another way to think of that is that the strong nuclear force captures those neutrons. And when the strong nuclear force captures those neutrons, it means that they're now within the nucleus, they're part of the nucleus, and we've basically created a different isotope. So in that situation, newly formed nucleus will increase in mass number, but not in atomic number. However, anytime we have a change in a nucleus, we're going to basically see that it's unstable, and in some cases it might be stable, but in a lot of cases we'll be producing, or the product will be an unstable nucleus. Now there's two types of neutron capture here that we need to be aware of, and that idea of the nucleus being unstable is an important one that ties into both of these. In a sense, these are sort of two sides of the same coin. It's just a matter of time, really. And what I mean by a matter of time is how quickly each of these processes occur. So the first one is known as the S process. And that's basically S standing for slow neutron capture. So we've already talked about the fact that neutrons are captured. We'll then just sort of take that a step further. So after a neutron's captured, it can undergo, or the nucleus can undergo beta decay. So if we consider that nucleus undergoes beta decay, the type of decay that we're talking about there is when a neutron becomes a proton, and then also a beta particle and an electron antineutrino are also released. So tying back into Unit 7 there. So if you can't quite remember beta decay, go back and have a look at that. But ultimately what that means, the atomic number is increased. So we've taken a nucleus and we've created an element with a higher atomic number, so it's a different element. The mass number won't have changed. But ultimately we've now got a different element, so this S process could occur again, another neutron could be captured, and so it goes through the same idea, and increasingly larger nuclei can then be formed. The other process is known as the R process, and again, as I said earlier, it's a matter of time here really. So the S process being slow neutron capture, the R process is rapid neutron capture. And in this case, what we're looking at is that if we have neutron dense situation, so lots of neutrons floating around, so if you think about the S process, it's fairly few neutrons. So in neutron dense situations, or scenarios where lots of neutrons are being produced in other fusion reactions, or the decay of elements or nuclides in a star, there's basically insufficient time for the beta decay to occur. So insufficient time for beta decay before another neutron is captured. So that then means that instead of having the beta decay occurring and then producing a new element, we end up with heavier elements of the same, heavier nuclides of the same element. So as such, heavier isotopes, so with far more neutrons present, but it's still the same element, and they are going to be built up fairly quickly. When we're talking quickly here, keep in mind this is all sort of relative, so the S process is not necessarily slow on the scale of the universe. We're talking just in terms of life cycle of stars, so it could still be years kind of thing. So once we have them built up quickly, they will still eventually undergo a succession of beta decays. And the reason for that is because they're highly unstable. So while it might seem like we're sort of talking about effectively the same thing, considering that we still have these beta decays occurring, what ends up happening is that the elements that are produced, or the nuclides that are produced, are different to what would happen in the S process. So by looking at the proportion of different elements, we can sort of identify whether the R process or the S process has occurred. Having said that, the fact that the R process will occur in neutron-dense situations, whereas the S process is where the neutron density is a little bit lower, there's obviously going to be a difference in the types of stars where we'll see the S process or the R process occur.